Okay, welcome back. This is AP1 Experiments, video 3. And we just got done with talking about the period of a pendulum. Well, let's look at the period of a spring. So the period, we know, is equal to 2 pi square root of m over k. So if we were to graph period versus m, we would not get a straight line. So we need to graph period versus the square root of m. Okay, and that should be, and again, if we have no mass, we probably don't have a period, so we'll just start that from 0-ish about, and we'll get a straight line. So then we'll have to rearrange this equation. The period is equal to 2 pi under the square root of k multiplied by the square root of m. Now we're in the form of y is equal to mx. Okay, and our slope down m will equal 2 pi over the square root of k. So you can use the slope in order to get k value from this. So very similar to our pendulum bulb that we did before. All right, next experiment. Let's talk about some rotational stuff. Okay, so here we go. Let's say we have a ball that rolls down an incline. Now remember what our directions are using right-hand rule. This one here is rotating in this direction here. Therefore, our angular momentum vector is pointing into the page using right-hand rule. Clockwise is a torque into the page. Counterclockwise is a torque coming out of the page. Okay, or a momentum vector coming out of the page. Either one. Just a quick reminder about that. Okay, so anyways, this is rolling down an incline. So what's our equation there? Well, we have GPE equals kinetic energy translational plus kinetic energy rotational. Why? Because the center of mass will be moving down the incline, but it'll also be rolling. So then we have mgh equals 1/2 mv squared plus 1/2 I omega squared. Well, I for a rotating disk is equal to 1/2 mr squared. And we know that omega is equal to v over r. So let's plug all this in here. So we have mgh equals 1/2 mv squared plus 1/2, and then we have to multiply that by 1/2 mr squared, and then w squared is going to be v squared over r squared. And let's cancel out everything that cancels out. So we then have an m that crosses off everywhere, and I see that the r squareds cross off. So we're then left with gh equals 1/2 v squared plus, that looks like 1/4 v squared. So there's our final result. So then the question we have, what would happen if I change the radius of this particular sphere or particular disk? Okay, what should happen to my final velocity at the end? Well, we see that radius, I'll just say, does not equal any difference. So let's put a not equal sign. Radius is not in my equation. What if I change the mass of this? Well, we see that mass is not in this equation, so there's no effect to the mass at all. Now, what if I change the shape of this and make it a triangle? Well, obviously that's going to affect it because, don't forget that a triangle doesn't roll very well. Okay, so we can conceptualize this, pretty well, and I think that should make good sense. Okay. Now, what about this thing rolling down an incline? We dealt with this in terms of energy, right? We could have thought about it in terms of friction. There is a friction force going this way against the motion of it, right? But don't panic. That's what's causing this to spin. Without any friction force there, this thing could not spin. Okay, it would just slide down the incline. Okay, which, by the way, would give it its greatest velocity. If there was no friction here and this thing just slid down, then we would not have the kinetic energy rotational. How does this look like with forces? Well, remember, force net in this case would be force gravity x minus the friction force. Now, even though that friction force is causing it to rotate, it does oppose the center of mass from just going down. So you would have ma equals mg sine theta, okay, minus mg cosine theta mu. And mg cosine theta mu, of course, would be equal to the friction force. So that's going to be ma is equal to mg sine theta minus force of friction. That could be mg cosine theta mu, or it could be some other force. We're not going to know exactly, depending on how we want to approximate the friction force for that. Now, that would be a static coefficient of friction, though, okay, because it's not actually sliding. It's causing rolling going on here, okay? But there's different ways of approximating that. And anyway, so that's the general concept there. You can look at this via energy or by forces. Either way, if this thing goes down the incline, rolling does use up some of the force or uses up some of the energy. Now let's make a comparison. What if I had a cart rolling down the incline like this? Okay. Would there be greater or less linear velocity? Okay. Well, the answer is going to be velocity here is going to be greater than something that rolls down if it has the same mass. And the reason is our rolling kinetic energy here, okay, is not going to occupy as much because this mass here itself isn't rolling. So this mass here is all going to go into kinetic energy translational. Okay, so what would our equation look like? We would have GPE goes into kinetic energy translational, and I'll do sub T for the mass of the cart here, plus kinetic energy rotational, and then plus kinetic energy translational. And these two are for the rolling wheels. This one is for the velocity of this cart here. So that would be greater linear velocity for a cart that has two wheels on it versus the whole wheel itself just rolling down the incline. So I just want to kind of go over that with you. Okay. So last but not least, what about moment of inertia? So if I have three different situations here. So I've got just a hollow rim here, and these all have the same mass. We want to look, what if I had spokes on this one here? Got little spokes like this. Okay, and let's say this one here is all solid. Okay, so I'll color that in. We want to rank the moment of inertias for each of these here. And again, they're all the same mass. Okay, the moment of inertia for this one, I, would be greater than the moment of inertia for this, which would be greater than the moment of inertia for this. Why would that be so? Well, remember our generalized equation, I equal mr squared. The farther the mass is from the center of rotation, the greater its moment of inertia. This one has all of its mass very far from the center. This one has some of its mass closer to the center, but most of it's still far away. Where this one here has a distribution throughout. There's a lot of mass close to the center of here. So if all three of these things have the same mass, this would have the least moment of inertia because there's a lot of its mass closer to the center of the circle. Okay, so that is it for movie 3. Another movie coming up.